Okay, section 8.8, exceptions to the octet rule. So we've learned about the octet rule. We've used it in our drawing of Lewis structures. Now we want to go over a few exceptions. It turns out there's some cases where it appears as though the best Lewis structures are ones in which the central atom does not have 8 electrons. So there's 3 situations here that we're going to discuss. One is the case where the central atom has fewer than 8 electrons, and that's particularly with beryllium and boron. And then in the second situation, we're going to talk about the case where the central atom has fewer than 8 electrons because we have an odd number of electrons. It turns out there are some chemical species that have an odd number of valence electrons. And then finally, there's the case where we have a central atom appears to have more, or greater than 8 electrons. So we're going to take one each time, one at a time. So let's try the case 1 of where we have fewer than 8 electrons. So this tends to happen. It appears to happen with just these 3 atoms. So beryllium, which is element number 4, boron, which is element number 5, and then aluminum, which is element number 13. Those are the 3 elements. So the way to show you this is to consider the experimentally determined chemical formulas of 3 molecules. Beryllium dihydride, boron trihydride, and aluminum trihydride, if you want to call them that. So the idea here is that if you draw the Lewis structures of these species, you don't have enough electrons to get an octet on the central atom. So remember, beryllium is in column 2A, so it has 2 valence electrons. Hydrogen is in column 1A, so it only has 1, so there's only 4 electrons to deal with. All 4 have been shown here in the form of single bonds. So the beryllium actually only has 4 valence electrons. So that can happen apparently. For the case of boron, BH3, boron is in column 3A, so it has 3 valence electrons. Each hydrogen has 1, so that's only 6 electrons. Well, we've already accounted for all 6. 6 valence electrons around the boron, right? Oops, let me draw it right there. So that's what we would call electron deficient structures. The central atom has fewer than 8 electrons. And we can see the same thing with aluminum. Aluminum is in the same column, the same family as boron. It's in column 3A. So it also has 3 valence electrons. So again, 2, 4, 6, we only have 6 valence electrons on that aluminum. So these are examples of what we would call electron deficient structures. It appears as though those 3 elements can form Lewis structures with fewer than 8 electrons. Now it turns out it might make them actually kind of reactive. It's a way to explain their reactivities, because it turns out if you take something like boron, which only has 6 electrons, and you put it in with ammonia, NH3, it appears as though a bond is formed between the boron and the nitrogen. Resulting in a formal charge of +1 on the boron. I'm sorry, a -1. My mistake, -1. And a +1 formal charge on the nitrogen. But that bond does appear to exist between the boron and the nitrogen. And our explanation for that bond would be that the lone pair on nitrogen is being used to bring that boron back up to 8 electrons, right? So now the boron has fulfilled the octet rule and has 8 electrons. So beryllium, boron, aluminum, those are the 3 species, the 3 central, talking about them from the position of being central atoms, where they can have fewer than 8 electrons and still form apparently somewhat stable structures. The second case is the issue of odd electrons. There are in nature substances which have an odd number of valence electrons, and they're called free radicals. A radical is a chemical species that has an unpaired electron, and so atoms that have odd numbers of electrons will have unpaired electrons, and they're called free radicals. So NO2 is an interesting one. Nitrogen is in column 5A, so it has 5 valence electrons. Oxygen is in column 6A, so it has 6 valence electrons. So we have 17 valence electrons here. So if you draw the Lewis structure for 17 electrons, so there's 4, get the surrounding atoms up to 8, so I've used 12. Now we're down to 1. Put that 1 right there on the nitrogen, because the surrounding atoms are already up to 8. Subtract that 1, and we're down to 0. So now the nitrogen has 5. 2 here, 2 here, 1 here. So I'm going to take a pair on the oxygen and push it. We use the double arrow to indicate that we're drawing a different Lewis structure. We now have a double bond. And look what happens. The nitrogen, this is as good as we can get. Each oxygen has 8. The nitrogen has 7 electrons. 7 valence electrons, right? That's an odd number. It's as close to 8 as you can get without reaching 8 based on how many electrons. We just don't have enough electrons in order to get up to 18 and then have 8 around the nitrogen. So this appears to be the most stable Lewis structure for NO2. But as I will claim, free radicals, because they have an unpaired electron and an odd number of electrons, it actually makes them reactive. The nitrogen has room for 1 more electron. So what will happen is if you take NO2, it'll react with itself to give you something called N2O4. And we can explain that based on this Lewis structure. If we take 2 NO2s and put the nitrogen atoms next to each other, look what happens. This nitrogen has 1, this nitrogen has 1. They can form a bond. And so what you get is a single bond between those 2 nitrogens, and then double bonds to these oxygens. And of course, we'll fill out all the lone pairs. So now everything's got a nice, neat 8 valence electrons. We've fulfilled the octet by combining those 2 NO2s, okay? So that's an interesting aspect as well. Drawing Lewis structures for odd number of electron species. So generally what you want to do is you want to get the surrounding atoms up to 8, and then get the central atom as close to 8 as you can. So 7 is as close as you can get, so that's what's generally observed. Okay? Now here's category 3 of our exceptions. It's often called expanded octet. Again, we're talking about the central atom. Okay, we're just talking about the central atom. We're not talking about the surrounding atoms. We generally do not observe more than 8 electrons around the surrounding atoms, but around the central atom we can. And so generally what's observed is once you get to the 3rd row, okay, the 4th row, or the 5th row in the periodic table, okay? So we're talking about elements like phosphorus, sulfur, chlorine, arsenic, selenium, bromine, tellurium, iodine, and even xenon. Okay, so third row, fourth row, fifth row of the periodic table. Starting with phosphorus. What is observed is that it is possible to have structures where there are more than 8 electrons on the central atom. So usually these occur when you have highly electronegative surrounding atoms. The highly electronegative surrounding atoms are fluorine, oxygen, chlorine. It can happen. So the example that I'm going to give you from your textbook is Sf6 Sulfur Hexafluoride. This is a famous example. If you draw the Lewis structure for Sf6, we have 6 surrounding atoms, right? So how many electrons do we have around the central atom? We haven't completed the Lewis structure. But at a minimum, if you look at it, this sulfur has to have 12 electrons because it has a bond to each fluorine. Sf6 exists. This is found. We can make this in a laboratory. It's a real structure. That means the sulfur has to have more than 8. So if one of these elements is in the central position and it has more than 4 atoms connected to it, it will have more than 8 electrons. Now I'm going to go ahead and fill out the actual accepted Lewis structure, and then I'll show you how this works in terms of the number of electrons. Remember, we're only going to add more than 8 electrons for the central atom, not for surrounding atoms. Okay. How many electrons would we expect? Well, sulfur is in 6A, and there's 1 sulfur, so that's 1 times 6. Fluorine is in column 7A, but there's 6 of them, so that's 42 plus 6 is 48 electrons. There's 6 surrounding atoms, so that's 12 electrons right there. So that gives us 36. So what did I do? I put 3 lone pairs on each of the surrounding atoms, and there's 6 of them. So that's 36 electrons, and you get 0. Okay? Interestingly enough, if you do a formal charge calculation, sulfur is 0. And as we said when we talked about formal charge, it's useful to have formal, or it's found that the stable structures are ones which the formal charges are close or equal to 0. So this appears to be the best possible Lewis structure. It's one which results in a formal charge of 0 for the sulfur atom. Okay? So that is not to say that sulfur is always expanded octet. For example, if we have this molecule here, sulfur dichloride, this one is not an expanded octet because there's only 2 surrounding atoms. And so what happens is if you do your electron of bookkeeping, sulfur has 6, chlorine has 7, that's 20, we've already used 4. So now we're down to 16, sorry. 2, 4, 6, get the surrounding atoms up to 8, 12, 14, 16. Here we have a nice octet. So it is the case that these elements can also be octet. It just depends on how many surrounding atoms they have. If they have a large number of surrounding atoms, it's quite possible for them to have an expanded octet.